Okay, so here we go. This is our first lesson, Physics 12. So I got my course outline here. We've already kind of gone through that. This should be at the front of your binder, organizing stuff. Your parent letter, if you need a paper copy of that, come grab one. I have them in my class. But as I tried to make a fillable PDF, so we'll see if that works. Now this, you should all have grabbed, or you will all have access to this. It is a formula sheet. I do want you to all have a paper copy of this. I do want you to put your name at the top of the thing, and I've got all these printed out the back of the class, so you can come get one from me. I will make a copy of this available in the Google Classroom as well. We're going to be adding stuff to it. The space at the back is going to function as your cheat sheet for the entirety of the course, but you're only getting one of these. It's not like you can do all of it, you know, load it up every time. I'm not going to give you a new cheat sheet every chapter. I'll explain kind of how that works when we get to our first test. But I'm going to be adding things to it. Eventually, your formula sheet is going to look something like this one. Sorry, one sec. It's going to look something like this. And it's going to be filled with all of these useful things. And you're going to have access to it. You can use your formula sheet. So I want you all to have one. I want you to have your name on it. And we're going to add the things that I add. I'm going to collect them when we do tests, and I'll take a look at what's there. And you're going to be able to use the space on the back to function as a cheat sheet for the course. So again, we'll get there. But come grab one of these if you haven't already. Here we go. Physics 12, Student Workbook, Part 1. This is actually less than Part 1. This is not even all of Part 1. This is just the first. There's an extra copy of the formula sheet on the inside cover. You need to reference it. This is the course that we're going through in its entirety, except we're not doing electric circuits. So I can start looking at stuff like this. We are not going to be doing this chapter, because you should have all done that with Morrison last year or earlier this year. Here we go. Vector kinematics. This will start very reviewy, so we're going to go fast-ish. Lots of this is stuff I would get you guys to tell me, but you're not here, so that's okay. Motion at a constant speed. Let's do some review. Motion at a constant speed means what? And this is where I hear all of you say, well, motion at a constant speed means that acceleration is equal to 0 meters per second squared. It is constant. And, well, I mean, an acceleration equaling 0 has a bunch of implications there. We'll get into it. So a vector quantity, bit of a review here. I think this should be a review of Physics 11. A vector is a quantity that has a magnitude and a direction. So a magnitude, you can think of a magnitude as something like a size, and your direction, up, down, east, west. Obviously there are more, but etc. Those are your, having both of those things makes this thing a vector. So vectors are things like, well, that have both of those, a magnitude and a direction. That includes things like, let's do it right like this. Things like displacement is a vector, which you should have looked at last year. Displacement is how far and which way have you gone from some origin. Acceleration is a vector. Velocity is a vector. Force is a vector. Okay. All these things you should have, should have talked about in Physics 11. These are vectors. There are many examples of vectors and scalars in physics. A scalar, I'm going to switch colors here. Sorry. scalar quantity has only magnitude, no direction. These are things like speed, distance, time, mass, energy, these kinds of things. They have no direction associated with it. They are just valued quantities. And like I said, there's lots of examples of both of these things, types of objects in physics. Position, given to us with this notation, typically, well, it's got an x with a arrow above it because position is also a vector, is the location of an object measured from some origin. Origin is a zeroed point, wherever it is you're starting from. A zero. It's measured, positions measured in meters, has no direction. Again, hopefully this is all review. Measured in meters, it has a direction. Because it has both of those things, it is a vector. The direction of the position can be given in words, things like east or west, north, south, up, down, left or right, forward or backward, that kind of stuff. Or it can be using a symbol. And I don't know if Mr. Morrison did this with you guys, but we're going to start using vectored notation for this. And the vector notation we're going to use is I-hats. That's a little letter I with a hat above it. This is typically the x direction. The y direction is j hat, we call it. So we go positive or negative j hat. So y direction. And then we're not going to be doing a lot of it, but you're going this year, but you will eventually. As soon as you start doing things in 3 dimensions, you need a z direction. Again, we won't do anything 3-dimensional this year, I don't think. Actually, I know we're not. But you know, should you need 3 dimensions, then you've got the k hat vector there as well. So you've got east, west, up, down, left, right, all those things, or you've got symbolic notation. I hats in the x direction, positive and negative. J hats, positive or negative in the y direction. K hats, positive or negative in the z direction. This is likely new to you, but I mean, I don't think it's terribly difficult to wrap your head around. So if we look at this guy here, we have an initial and a final position, including the direction of that person. So he's not moving. He's just, well, he's located at 2 points. We don't know how he got there, but we've got a starting position here and an ending position here. We just want to write down where he's at. So his starting position, if this is our 0, starting position is at 10, 11, 12, 13, 14. We can write it one of 2 ways. You can say 14 I hat, or typically east is positive, west is negative. Right is also typically positive, left is typically negative. So we could say something like he's, oh, and that should be meters, so we need the units there, or 14 meters to the right. And this ending position down here, he's at negative 5 meters. That's 0, 1, 2, 3, 4, 5. Negative 5 meters I hat. Or you could just say he's 5 meters left. Or you could have said 5 meters west. We'll go back up here. We could have said 4 meters east. Because the question doesn't specify. It just, we know that he's left and right of 0, whatever that means. So 3 different ways to write each one of those. Now, position's easy. Displacement's the next one. Displacement is a change in a position. The letter we use to represent a change in, you all saw in Physics 11. A change in a position looks like this. It is a D with an arrow above it. It is equal to, means it's equal to a change in a position. Change is delta, that is that Greek letter. It's a change in a position. And to figure out your change in a position, it's your final position minus your initial position. Displacement, because it is a change in position, has a direction and it has a vector from the initial position to the final position. In physics, the symbol for changing, we already said all this, but we have the delta. So delta x. The distance is a scalar quantity that has no direction, and it represents the total meters an object traveled. But the displacement is a vectored quantity because it's the change in a position. Distance is scalar, displacement vector. Again, this should all be reviewed. So in this example down here, I've got this guy. Here he was at 14. Now here he is at 5. So what happened here? He moved 14 and then he moved 5 more. So let's actually, again, this is going to look stupid because I'm going to do all of the work, but that's okay. Humor me. It's a change in a position. So it's a final position minus an initial position. I do want you to get into the habit, even for simple questions, of writing it out like this, step by step. So his final position was -5 I hat. His initial position, so minus his initial position, which was 14 I hat. And that's going to give us -19, and I forgot to put the units there, so we'll put the units in there now. -19 meters I hat. Or we could write that as his displacement was 19 meters to the left. You don't want to include both of those. So you want either -19 I hat or 19 to the left. If you said -19 to the left, well, negative left is actually right, and so that would be problematic. The distance, so that's displacement. The distance traveled doesn't care about direction. All it cares about is how far this object moved. The distance itself would just be 19 meters, and distance is always positive because negative is just a direction. So that's it. From the page, relatively straightforward, I think. Let's faster. Is the distance and the displacement had the same magnitude in the previous one? The magnitude of the displacement was the same as the distance. They were both -9. They were both 19. Is this always true? Pause the video, think about it for a second here. The answer to that question is actually no. This is not always true. If you go back and forth, distance increases. Displacement may not. For example, if I started here and went 5 meters this way, and then I went 4 meters this way, the distance is 9, but my displacement is 1 I hat. Right? Is the magnitude of displacement always the same as the distance? Well, we've already established that. No. And there will be questions like this where you have to explain it, even something as simple as a diagram like this. Another example would be something like this. If the start and the finish line were the same line, i.e. you're running around a track, your distance would be, you'd be increasing the entire way. Maybe you ran 800 meters around the track, but your displacement is 0 because your final position and your initial position are the same. Throughout this workbook, in almost every lesson, we're going to go through conceptual questions like this. I would recommend you think through them on your own first. Pause the video, mull it over for yourself. The reason for that is these questions are based on misconceptions that students typically have about the physical world. The hardest part about Physics 12 is you guys think you understand what is going on when you look at a relatively simple system in the world, and that 99% of the time, actually it's not true, maybe like 90% of the time, that's actually wrong. Your ideas of how things work are incorrect. And so Physics 12 is all about unlearning and then relearning how things actually are. The reason that we work on questions like this is to try and correct these misconceptions. It is also worthwhile communicating ideas using the vocabulary of physics, since it's going to help us in the long run understand it better. So that is the first one of these kinds of questions, but there's a lot of these. Flip the page. So the displacement, delta x, delta change in position, will have the same value as the distance d unless there's a change in direction. As soon as the direction changes, now our displacement and our distance are not going to be the same thing. In which case, we need to apply the definition really, really carefully, which we've already kind of done. Let's do it again. I want to find the displacement and the distance of a person who starts off at positive 14 I hat, then walks to negative 5 I hat, then walks to 2 I hat. To find the distance is always adding. So the distance from 14 to 5 is 19 meters, and he walks another 7 meters. So the distance traveled is going to be that 19 plus 7 is 26, and I need my units meters. But when we look at displacement, we don't care about the middle of the path. All we care is about the beginning and the end. So there's that. I got my beginning. There's my initial position, x initial, and I've got my x final. Got my subscripts going on. So displacement is change in position, which means I got a final position minus an initial position. My final position is positive 2, because it's 2 to the right of 0. So it's 2 I hat minus, and his starting position was 14 I hat. 2 I hat minus 14 I hat is negative 12 I hat, and I'm going to put meters there at the end. So actually, I shouldn't write it like that. I'm going to write it properly here. Negative 12 meters, units, and then direction I hat. And so, I mean, it goes without saying. I mean, it's obvious he moved to the left, but this is how you show it with using the proper notation. His displacement was negative 12 meters I hat. He ended 12 meters to the left of where he started. You can think of this as net movement. You talked about net forces before, so sum of all your forces. The net movement is something where you can think of displacement. To always write this notation is time consuming, so we're just going to condense it. We're going to call it this. Displacement is d with an arrow above it. Distance is d without the arrow above it. So notation is going to get picky. If it's a vector, you got to have the arrow, and if it's not, well, then you don't. Velocity, you guys have already seen. Velocity is v with the arrow above it. That is a vector quantity, has a magnitude and a direction. We use the same directions, I hats, j hats. Speed is v without the arrow above it. Is a scalar quantity, has magnitude only, no direction. The magnitude of velocity is speed. And that's an important relationship to understand. And then yeah, I'll leave it at that. So if I've got constant velocity, this is the kinematic equation you should have seen before. My velocity v is equal to my displacement d divided by the amount of time it takes for that to happen. Flip the page. So this whole page is just this example 5 here. For this guy, if my velocity is positive 5, it should be meters per second I hat is how I typically write things. Or 5 meters east, we're going to interpret this ratio. What does it mean for something to have a velocity of 5 meters per second? Well, what that means is this. Every second, you travel 5 meters. And in this case, the direction is to the east. B, we've got a chart here that we can use to represent that. At 0 second, our position is 0 meters. At 1 second, our position is 5 meters. 1 second later, at the 2 second mark, our position has changed. It is now 10 meters. Position also needs a direction. This position is a vector. At 3 seconds, we've gone 5 more meters. So it's 15 meters east. Again, this should all be straightforward. And a review. So that's A, that's B. Now we can draw a position time graph. Here we go. There's my number line at 0. There he is. At 1 second later, he's at 5. T equals 1. T equals 2. T equals 3. Here is our dude. We can graph this too. Position time graph, which you should have done in Physics 11. At 0 seconds, he's at 0. At 1 second, he's at 5. At 2 seconds, he's at 10. At 3 seconds, here he is at 15. And then we can connect these dots. And there we go. We've got a position time graph of our guy who's moving. The slope is equal to the rise over the run. Well, that's just, if I look at the rise, a rise is a change in position. The run is a change in time. Well, a change in position, that's just displacement. Change in time, well, that's just the amount of time it took. That's velocity, which again is review, should be review. The slope of a position time graph is the velocity. So in this case, if we've got constant velocity equals a straight line on that graph. If we take that graph and we, if I increase the steepness, if I have something like that, what does that mean? Pause it for a sec. Tell me, what does that mean? Well, if a steeper line means more position is changing in a shorter period of time, which means we've got a higher velocity than the pink line. Or if I've got a more shallow slope, my slope is lower, that means I've got a slower velocity. And then the last one, we're going to produce a velocity time graph. There's D, we've done E. Here's F. The velocity time graph. Well, what's happening with the velocity? Every second the velocity remains the same. The velocity is 5 meters per second squared east, and that doesn't change. So here we are at 5, positive 5 meters per second. For those of you who are in calculus, I know it probably hasn't happened yet, but you're going to learn about derivatives. And you're going to, one of the things that you're actually going to see is that velocity is the derivative of position. Which, yeah, the connections between, and I'm going to be showing you lots of the connections between calculus and physics as we go. For those of you who are in calculus, this will mean something to you and hopefully be interesting. For those of you who are not in calculus, you'll see it one day eventually. Don't worry about it. Just nod and say, yes, that was interesting. Off of the page. Do this one quick here. I don't need to necessarily do all of the interpretations. I've got a velocity of a negative 3 I hat, so my position is changing. 1 second later, I'm going to be at negative 3 I hat, or we could say 3 meters west. 2 seconds, we're going to be at negative 6 meters I hat, or 6 west, meters west. Just put units in there. 3 seconds, we're going to be at negative 9 meters I hat, or 9 meters west. So this, and the, yeah, you get it. The important thing I wanted you to see here, though, is what that does to these graphs down here. I'm not going to draw these, but we're going to draw these. So what I, again, want to remind you of is that a negative slope on a position time graph means the object is moving in a negative direction. It doesn't tell you where it is, it just tells you the direction that it's moving. So what that's going to look like on a velocity time graph, my velocity is always -3. So here we are, it's a flat line at -3 meters per second on a velocity time graph. There it is. So we can see the velocity is the slope of a position time graph. Should be an arrow above that. And we can interpret the positive or negative slopes as indicating the direction of motion. If there is no direction changes to worry about, we can write a more simple scalar equation relating speed and distance. Speed is equal to the distance d over the time t. Cross multiplying, you get something that looks like that. That's expression for the distance, or you can find the time. This is stuff that I did with my pre-diploma math 9s. You guys should be able to do that. You've all seen this. We'll throw it down here. Some of you find this thing useful. We've got the DVT triangle. It also works for position. We just make, or sorry, for velocity. We just have to make these two vectors. And again, this is true for constant velocity only. We'll bring in the acceleration later. This is going to be a review of stuff you've seen before. And I want to make sure that we know how to go from kilometers per hour to meters per second. If you were here, I'd ask you the question, but you're not, so I'll just assume you know how to convert. To go from kilometers per hour to meters per second, you divide by 3.6. To go the other way, you multiply by 3.6. Something you're going to want to remember if you have forgotten it. Some more exercises here. Example 7. So here we go. Car is moving 150 kilometers per hour. It moves for 2 seconds. How far does it go? Something you've seen before, but again, it's a simple one that we're going to go through just to get to used to how I want you to do things. So the first thing I always want to see, any question you're going to do is you draw a diagram. So here we go. Got my car. It's going that way. Initial position, my final position, it's over somewhere. Somehow it got longer. So let's add the information that we know. We know that the velocity of the car is 150 kilometers per hour. We know that the time is 2 seconds. So I've got my list of information. So I've drawn my diagram. I've written down what I know. I want to see this every time. I'm going to get kind of picky. We want to find its displacement. We want to find how far it went. Write down what you have. Write down what you want to find out. Then we need to make sure that we're in standard units. So meters, kilograms, seconds, those are scientific standard units. That's what we want to make sure we're in. We are not. We've got 150 kilometers per hour. To go from kilometers per hour to meters per second, we want to divide by 3.6 because this guy's also in seconds. So we've got seconds here and kilometers and hours here. We don't want things, we do want to make our units consistent. So we're going to get that this thing is traveling with a velocity of 41.67 meters per second. We've already figured out what variable we're looking for. The physics relationship we're going to use, that's our formula. We're going to use this guy here. I want to find our displacement. That's equal to our velocity times our time. And now we're going to fill the thing in. This is equal to 150 meters per second times 2 seconds. If you look at the units here, you do this in chemistry all the time. If I have meters per second and I'm timesing by seconds, my seconds are going to cancel. So we got units that are meters, which is what we want. then we've known we've done something correctly. That's, oh, guys, if you were here, you'd have all corrected me, right? It's not 150 meters per second. It's 41.67 meters per second. And my seconds cancel. And so I'm going to get that this thing moved a distance over, had a displacement of 83.34 meters. And based on my drawing, it's positive. So I hat. We found our answer. Now this one down here. This is the one I don't care about in physics 12. We approximate so many things. Ropes are massless. Cows are sort of spherical. We ignore so many things. And so when we talk about sig figs, they don't make a lot of sense unless you're doing labs. Sig figs are only important when doing labs. In physics. Okay. There you go. That's the procedure. That's what I want to see every time. Draw the picture, write down your variables, look at what you're trying to isolate, convert where you need to convert, write your formula, fill it in, and get your answer. That's what I want every time. There's another way to do some of these things, and I don't know if you did stuff like this with Mr. Morrison. When we have two objects that are moving relative to each other, it is often convenient to determine something called their relative speed. Important concept to talk about now, because we're going to talk about, when we talk about special relativity, this is going to show up again. So for objects going in the same direction, this will be the difference between their speeds. For objects going in opposite directions, the relative speed is going to be their sum. Show you what, like, we'll see how that plays out. So if I've got someone going 40 kilometers per hour, and for those of you who have your driver's license, this is easy to picture. If you're going the same speed as the object in front of you, the relative speed between you guys is 0. It's no different than if you were both just stationary. But if you're catching up to them, if you're going 40 and they're only going 20, your relative speed is the subtraction of these. It's 40 minus 20. It's you, because you are sneaking up on them at 20 kilometers per hour. If you're going at each other, it's no different than at 40 and 20. It's no different than if one of you were stopped and the other one of you were driving at 60 kilometers per hour. This one example right here is why head-on car collisions are so dangerous, because you might only be going 50 kilometers per hour, and so is the other guy. So if you're going 50 and they're going 50, that's a head-on collision. That's like hitting a concrete wall at 100 kilometers per hour, which is why speed limits are important, and we care about stuff like this. So you could reference these things differently. If the relative speed is 60, maybe this isn't 40 and 20. Maybe this is 60 kilometers per hour and 0 kilometers per hour. Okay. Using relative speed allows us to solve questions like this relatively easily. If this is doing a standard kinematics equation, this question would suck. I got two trains. How long does it take to completely pass each other? If you're doing this without using relative velocity, the first option is a set of, or I shouldn't say a set of, I should say a system of equations. A whole bunch of equations. You run them together and you're done. Or we can use relative velocity. Your second option is to use relative velocities. And if we do that, that becomes a lot easier. So instead of 13 and 5, we could say, okay, well, the relative velocity between these guys, well, let's write it. We've got the picture made for us already. We know that, I'm going to say this, the relative velocity, because they're going the same direction, I'll call it V sub rel, is 13 minus 5 which is 8 meters per second. That's the same thing. That what that means is this guy's effectively going 0, and this guy's not going 13, he's going 8. This is the same problem, okay? So our relative velocity is 8 meters per second. Our time is what we want to find. We know the distance. It doesn't look like it does, but we do actually. So let's see, look what's happening here. Our distances, or our displacement, that the train that's actually moving in our relative state, we can see what's going on here. We want the front, starts at the back of this train. The front of the train moves 100 meters. To get to this point here. And then, well, how much further does it have to go? Well, to go from here to here, it went 100. Now, to get the back of the train in front of this guy, we know this train is 150 long. So that's 50 meters. This is 100 meters. So to get the back of the train to the front of this train, that's another 150 meters. So this guy to the front, that's 100 meters. This guy from the back to the front is another 150. So our total distance traveled by the train has to be 250 meters at a relative velocity of 8 meters per second. So now we can just run this thing through. I want the time, so this is my equation. Our time is equal to our displacement divided by our velocity. Our displacement is 250 meters. Our relative velocity is 8 meters per second. That's going to give us a time of 31.25 seconds. So using relative velocities, that makes this thing a lot easier. That's lesson 1. A lot of this should have been a review from last year. Just getting you guys back into these ideas. The next couple lessons are going to look at several different constant speeds. We're going to look at acceleration, then we're going to look at the standard kinematics equations, and then we're going to start using vectors. So this first chapter just gets you guys easing back into where you were before. Your homework for this chapter are the following questions. You're not going to do all of these exercises. There's 2 pages here. I want you guys to do the following. I want you to do 1 to 3 and 6 to 12. 1, 2, 3. 6, 7, yeah, 6 to 12. So there's a fair bit there. I'm only going to post 1 video just to get you guys into it. Starting on Monday, there's going to be 2 a day, and away we go. As always, comments, questions, concerns, feel free to send me an email or come drop in. I'm looking forward to meeting all of you.